Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture, we have seen the mechanism behind the formation of precipitation. Two different processes behind the formation of precipitation are lifting of air masses and nucleation. Under lifting of air masses, we have seen orographic lifting, that is the precipitation which we are getting near the hilly areas and mountainous regions is due to orographic precipitation. Second one is the frontal lifting, and third one convective lifting. And after that, nucleation of the water vapor to form the clouds. After seeing these two processes, we have seen in depth mechanism, what is happening within the mechanism related to the cloud, what is happening within the cloud. We have seen a elaborated picture of cloud, and we have seen different processes taking place within the cloud. In that, water vapor is getting lifted up, and after that, after reaching certain level, they will be mixing up with so many water vapor particles coming down, grouping together and coming down as precipitation. Again within the cloud itself, breaking of the water vapor will be taking place. So, these things we have seen in details. Now, let us see how these particles are coming down. These particles should attain certain velocity in order to come back to the ground surface. So, in today's lecture, we are going to see the velocity with which the water vapor or the water vapor after condensation is coming back to the ground surface. That is what is termed as terminal velocity. So, let us move on to today's lecture. Terminal velocity. What is meant by terminal velocity? You consider a spherical raindrop. Actually, these raindrops will not be spherical. It is our assumption that let it be spherical in shape. Initially, it will be having some acceleration. After that, what will happen? It will attain a constant velocity, and that velocity is termed as terminal velocity. So, the velocity with which the constant velocity with which the raindrop is falling onto the ground from the atmosphere is termed as the terminal velocity. Now, consider a spherical drop and let the diameter of the spherical drop be d. We are going to consider a spherical raindrop which is having a diameter d. Now, let us see what are the different forces acting on the raindrop. Different forces are acting on the raindrop, and because of that the drop is falling down. So, let us see what are the different forces acting on the raindrop. First one is due to gravity force. So, due to gravity force, what is the force? That is the weight of the drop which is acting in the downward direction. So, gravity force is mainly due to the weight of the raindrop. Then second one is that is acting in the downward direction. Second one is buoyancy, buoyant force. Buoyant force is due to the displacement of air by the drop. So, as it moves, as the raindrop is moving within the fluid, here in this case it is air. How much is the air displaced by the raindrop? That is mentioned as buoyancy force. So, that is due to the displacement of air by the drop. That will be acting in the upward direction. Gravity force is acting in the downward direction, buoyant force is acting in the upward direction. Now, one more force is there. These two are body forces. And third one is the friction drag force. What is meant by drag force? We have already studied in fluid mechanics. Drag force is due to the resistance offered by the air or friction between the drop and the surrounding air is causing the drag force. This drag force is also acting in the upward direction. This is drag force. So, we are having totally 3 forces: gravity force, buoyant force and drag force. We need to have the expressions for gravity force, buoyant force and drag force. After that, we will write the expression for equilibrium condition for finding out the velocity with which the drop is falling down. So, what is the expression for gravity force? It is actually the weight acting in the downward direction. That is, gravity force is given by, what is the expression for mass? We can write it in terms of density. Mass is equal to density multiplied by volume of the drop. But here we are talking about the weight. So, density multiplied by acceleration due to gravity g multiplied by volume of the drop. What is meant by density multiplied by gravity, acceleration due to gravity? That is rho g. Rho g is nothing but the specific weight. We were using the notation gamma in fluid mechanics, but here we will write it in terms of rho g. So, here in this case, drop which we are considering as water droplet, right? So, it will be having the density of water, so that we are going to represent by means of rho w. So, Fg can be written as rho wg pi by 6 d cube. Now, coming to, that is, rho w is the density of water. Now, coming to the buoyant force, force due to buoyancy. That is the weight of air or fluid which is displaced by the airdrop. In this case, air is getting displaced by the raindrop. So, the similar expression, buoyant force also will be having the similar expression, but instead of density of water, we will be having density of air. So, Fb is given by rho a g pi by 6 d cube. So, here in these two cases, pi by 6 d cube is representing the volume of the drop, that is, in the case of gravity force, volume of the water droplet or the raindrop, and in the case of buoyant force, it is the volume of the air displaced by the raindrop. Here rho a is the density of air. Now, we need to write the expression for drag force, frictional drag force. Drag force is a, you can, from the name itself it is clear, it is due to the resistance of the air, resistance offered by the air. So, that is a surface force, it is acting on the surface area. Other two forces were body forces, this one is the surface force. So, Fd is given by the expression Cd rho a v square by 2. I am not going to derive the expression for drag force, this you might have already seen in the subject fluid mechanics. So, that expression directly I have taken here. Drag force is directly proportional to square of the velocity with which the drop is moving. So, drag force is given by Cd rho a v square by 2. Cd is the dimensionless drag coefficient and V is the velocity of fall. Then comes the area. A represents the cross sectional area of the raindrop, that is, we are considering the spherical drop. So, in that case the cross sectional area will be of circle, that is nothing but A is equal to pi by 4 d square. So, for equilibrium condition we will write the expression That is, initially we are considering the drop is released from rest, and initially it is with certain acceleration, and after that it will reach a uniform velocity which is termed as terminal velocity. We are representing this terminal velocity with the notation V subscript T. When it attains terminal velocity, all these forces will be in equilibrium condition. The expression for that we can write, so three forces will be balanced in that condition, and we can write the expression as Fd plus Fb. We are having two forces in the upward direction, Fb and Fd, and gravity force is acting in the downward direction. So, we can write the condition when the forces are balanced as Fd plus Fb is equal to Fg. After that, what we will do? We will substitute the expressions for each and every force in this equation. So, Fd can be written as Fg minus Fb. This is for simplicity only, because you know Fg and Fb are of similar expression, only with the difference of density of water and density of air. So, that we are going to substitute here. So, Fd is given by the expression Cd rho a pi by 4 d square Vt square by 2. We have written in the previous expression, that is V square by 2. Here at the balancing condition, when all the forces are in balance condition, V is replaced by terminal velocity Vt. So, this is equal to Fg minus Fb. Fg is rho Wg pi by 6 d cube minus rho Ag pi by 6 d cube. We can simplify the right hand side. It will be rho W minus rho Ag pi by 6 d cube. Now, we can cancel out certain terms from this equation. Pi gets cancelled, then comes d square gets cancelled, and we are having 2 on the denominator, and it will get cancelled, and it will be taking the form Cd rho a Vt square by 4 is equal to rho W minus rho a g d by 3. Again we can make, we need to have the expression for terminal velocity. For that we will make readjustments with the terms. So, Vt square is given by 4 by Cd rho a rho W minus rho a Gd by 3. So, we can write the expression for Vt as 4 by 3 Gd divided by Cd rho W by rho a minus 1 all to the power of half. So, here we were having Vt square. So, when the expression comes for Vt, we will be having under root. So, this expression will give you the velocity, terminal velocity, that is the velocity with which the raindrop is falling down onto the earth's surface. Now, let us look at the expression carefully. We are having Vt on the left hand side, diameter of the raindrop on the right hand side, and Cd also on the, that is coefficient of drag is also on the right hand side. So, you can understand that Vt is directly proportional to diameter of the particle, because d is coming on the numerator. And when you look at Cd, Vt is inversely proportional to Cd. So, Vt is directly proportional to d, that is, as d increases, terminal velocity also increases. When it comes to Cd, Vt is inversely proportional to Cd or directly proportional to 1 by Cd. So, as Cd increases, Vt will be decreasing, or Vt increases as Cd decreases. So, these relationships you should understand. As the diameter or the size of the droplet increases, definitely the velocity with which it will be falling will be increasing. And at the same time, if the resistance offered by the air is more or Cd is more, what will happen? Vt will be less. Velocity with which the drop is falling down will be less. A raindrop will be in spherical shape, approximately up to a diameter of 1 millimeter. So, if the rain diameter, if the size is beyond 1 millimeter, it will not be spherical in shape, it will be taking oval shape. So, when we were talking about the drag force, we were having a term A corresponding to the cross sectional area of the drop. So, in that case, we will not be able to substitute exactly pi by 4 d square. We have to take the equivalent area of the spherical cross sectional area corresponding to a oval shape. That is, if one raindrop size is greater than 1 mm, it will be oval in shape. So, that you need to take into account what is the size of the raindrop given to you. If it is less than 1 millimeter, directly you can take the cross sectional area as pi by 4 d square. On the other hand, if it is greater than 1 millimeter, we need to find the equivalent diameter of spherical raindrop having the same volume as the actual drop. Sometimes we approximate assuming it to be spherical, but majority cases that approximation is valid only up to a diameter, up to a size of 1 millimeter. Beyond that, it will not be spherical in shape. So, that much about terminal velocity. Now, we know with which velocity the raindrop is falling down. So, depending on the forces acting on the raindrop, that is the gravity force, buoyant force and the drag force, we can calculate the terminal velocity, that is the velocity with which the drop is falling down onto the ground. So, that much about terminal velocity. Here I am winding up. In the next lecture, we will see the intensity of rainfall, that is what will be the intensity of rainfall which we are experiencing on the ground. So, that can be explained by means of a thunderstorm cell model that we will see in the next lecture. Here I am winding up today's lecture. The reference corresponding to this terminal velocity part is from Ventichow and others applied hydrology textbook. Thank you.